Alright, so today's lecture will cover the first module, Electrical Engineering Basics. This module might take about 2 or 3 weeks to complete. We start off with understanding the electrical engineering basics because that will be the foundation for us to understand the workings of wind energy integration into the larger electrical systems, a transmission grid, if you want to say that. But before that, we need to if you're not really comfortable with electrical engineering principles, this module should be able to help you out with that. Um, the first thing that we see here is the way that the electrical grid is broken down into. There are three sectors that you can see here. The first one is given by four. We have the generation, the transmission, and the distribution, and the customer. The generation side is any units that produce electricity. It could be a coal-fired power plant, a nuclear generation plant. Then you have wind farms as well will come under generation units or generation station, and then large scale central power generation units are typically connected to transmission lines, and then you transfer them across long distances before they step down to voltage levels that can be consumed by customers, right? Any voltages, usually the customers, if you're talking about residential customers, they typically go down to 120, 240 volts. If there's a large industrial customer or even a large building, they can, voltages can rise up to 4 kilovolts to about 26 kilovolts or 69 kilovolts as well. The basic idea of this representation of an electrical grid into the circuit diagram is to let you guys know that an electrical system can simply be represented into elements such as resistors, which is given by this this kind of a W-shaped symbol here, which is a resistance, and then inductors, which are like a inverted W or shape symbol, which will all be explained in the coming slides. But a resistance inductor can represent an electrical line or even a load as well, and then some of the other elements like capacitors are represented by these two parallel lines, and a voltage source is any generation unit. So if you have to represent the entire system, entire grid system, they can simply be represented by a source, a resistance, an inductor. And what helps us while we represent these elements in a circuit diagram is figuring out, if we build this, what is the current flow across or through each line, and we'll also understand what the voltage is across an element, so that by representing the system by elements such as resistors, inductors, and a voltage source, you'll be able to figure out the power flow or the flow of current simply. That's the reason why we have to represent electrical systems into simpler circuit diagrams such as these. Alright, now we're getting into some important parameters, electrical system parameters. The first element that you have to understand is voltage. A voltage is nothing but an electromotive force that pushes electrically charged particles. So the equivalence of a voltage in mechanical terms would be, or mechanical domain would be, a pressure or an elevation. Assume the flow of fluid, right, as the flow of charges. So what do you need to allow flow of charges, flow of fluids? You need pressure. So that's for in terms of electrical systems, a pressure is equal to voltage. A voltage is represented usually in a DC or direct current with a positive and negative terminal. So if you, I mean, if you must have worked with your battery cells or even your car batteries, right? So you always have positive and negative terminal, and typically the voltage levels can be 12 volts. So by measuring the positive and negative terminals, you can measure the voltage across the source. So that's how you understand what a voltage is. It can be direct current or alternating current, a type of a source. And then you have the symbols which represent voltage. Either they can be represented by E, or most likely you'll represent them by this letter V. So voltage, again, in terms of mechanical terms, it's equivalent to pressure, and this is what pushes the electrons through electrical lines, resistors, or anything that you need, through which you need to push electrons. You need voltage. So voltage is equals to pressure, and then voltage is represented by the symbol V, and the units for voltage is volts. And then there are different formulas here, or equations, by which you can calculate the voltages for different shapes. We'll get into what a sinusoidal wave shape is. This is an alternating current wave. So in order to represent an alternating current, because as you can see here, an alternating current voltage will have a peak, like a high peak, and a negative peak. For example, if it can be plus 12, negative 12, and then 0. So you can see that the wave in alternating current is oscillating with respect to time. On the y-axis you have the levels, on the x-axis you have the time. So with respect to time, since the voltage values are varying, you need to represent that with a constant term, and that's when we make use of something called as voltage root mean square, and we'll get into that in the coming slides when we get into AC circuits. But then just understand here that in order to calculate voltages, you can make use of the root mean square equation, or root mean square equation. So hopefully that gives you an understanding of voltages. These principles are really important for you to move forward in this course. Some of these terms I'll keep repeating them, but a good understanding of this will help you in getting into, when we get into the large scale grids. This will help. Essentially, whatever you see in smaller circuits applied to the larger grid system as well. You have the voltages, you have the current flows, you have resistance, inductors, all of them. Whenever, you can work on a lab scale circuit. The same circuit can be a representation for a large scale electrical system, which you see is connected to, for example, a wind farm, connected to distribution systems. All those can be represented by small scale electrical circuits. And then we get into currents. What is current? Current consists of the movement of electrons, ions, and simply charged particles, right? So again, as I had mentioned, you need voltage in order to push electrons. And the flow of electrons is simply current. And the movement of electrons can either be can be in the form of vibration, or can be unidirectional. When we talk about oscillating flow of current, that's represented by a sinusoidal wave with respect to time. So the levels keep changing with respect to time, whereas a direct current will have a constant value with respect to time. So it could be just a value of 12, but an oscillating wave will have plus 12, it will be 0, and then negative 12. So it will keep varying between 0, 12, negative 12 values. Negative 12 is this right here, and this is positive 12, and this level is 0. So if you're familiar with x and y axis diagrams, that's how you can represent oscillating wave shape. And as I mentioned, DC electrical current is analogous to fluid flow in a mechanical system. So fluid flow is representation of electrons in a electrical circuit. And just like what I discussed in the previous slide, current, when it's oscillating in nature, can be represented by a constant horizontal wave by calculating the root mean square. And usually current is, the symbol for current is I, and the units for current is amps, or amperes or amps, simply amps. And the simple way to represent 1 ampere of current is the change of 1 coulomb of charge per second. So 1 coulomb of charge per second is 1 ampere, and the rate of change of fluid is in terms of current, in terms of mechanical mechanical domain, will be the rate of change of fluid, and the rate of change of charges is current in electrical terms. So hopefully that gives you a good understanding of the difference between voltage and current. Voltage is equivalent to pressure, current is equivalent to a flow of fluid. And now let's get into the elements. Elements or passive, simply passive elements are we'll get into that. It's essentially, it's an inherent property of a conductor, or even anything that is a material will have resistance. It can be an infinite resistance, or it can be a low resistance. The lower the resistance, the freer the flow of electrons. And usually conductors will have lower resistance and allow the flow of current through it. Alright, so resistance is a property of a material that opposes or resists the flow of current. So here, this is a good example, right? A cartoon which shows you, volts here is trying to push amps, but ohms is resisting the flow of amps through the conductor or a cable, right? So ohms or resistance, that's the ohms is the units for resistance. And the higher the resistance or higher the ohms, the lesser the current that flows through a conductor. And just like what we showed for mechanical systems, voltage is pressure, current is the flow of fluid, and resistance is equal to friction in mechanical domains. So the resistance in conductors is undesirable. So the lower the resistance, the better. So higher the resistance, the more the electricity that gets wasted in the form of heat. So resistance is equals to voltage divided by I, or if you rearrange systems, voltage is equals to I times R, and this is also called as the Ohm's law. So the Ohm's law is V equals to I times R, and so this is one of the most important formula for any electrical engineer, or any electrical person will tell you this is the most critical formula that they use, and if you understand this, we can move forward with more and more principles of electrical energy in terms of power and all that terms. But we just have to understand this. This is a critical formula. Voltage is equals to current times resistance. And the resistance can also be calculated if you know the resistivity of the conductor, the length of the conductor, area of cross section of a conductor. So for example, you can see here this is a key conductor, and area of cross section is the area of the circle, and length is the length of the cable, for example. And Rho here is the resistivity of the conductor. So if your typically conductors are made up of aluminum, copper, and little time and silver, even though it's expensive, has better conductor properties, but it's just too expensive, so people will, I mean, anyone would not want to you use silver in as a material for conductors, but silver is usually has a very low resistivity, and typically what we see in large scale electrical transmission systems are a combination of aluminum and copper. So typically the core of a conductor is made up of aluminum, and the outer region is made up of copper. So we'll get into that when we get into electrical lines, but I just wanted to let you guys know is that rho is a property of different materials that you use. So you want to make sure that you have less resistivity in order to make sure that the resistance is low, and also you need to make sure that the material that you use is not too expensive. So there's a cost and probably efficiency balance that you need to reach in order to ensure that that whatever you're using as a material is not too expensive, but at the same time it has good properties to ensure better flow of electricity. Alright, so hopefully these are, if you talk about electrical engineers, they'll tell you that typically the most important parameters that you need to know are voltage, current, and resistance. So if you understand this, we can now move forward with other things. Before this, okay, I can just get into using MATLAB. So now let's start getting into MATLAB. Alright, so I already have MATLAB open, but I've already also given you instructions to install MATLAB. So I'll not click on this because it's already opening, but I have MATLAB open here. And let me do one. Okay, so I have when I click on MATLAB, the icon, this program should open for me. So what we are going to make use of is nothing to do with scripting language. We're making use of user interface or graphic user interface or GUI based modeling of voltage source, a current elements, resistors, and all that. So first thing that you have to go here is go to Simulink. Click on Simulink when you enter MATLAB. And now you have many options here. What you have to do is click on blank model. So when you click on blank model, you now have a blank page open. So when you have a blank page open, this means that you can start dropping in elements in order to draw your circuit. And what we're trying to do here is create circuit diagrams and simulate the flow of electricity with respect to time, and then this will help us better understand symbolically what the flow of electrons look like, what the voltage drops are, and all the things that we'll get into in the coming classes. But let's start with a simple diagram, a voltage source and a resistance, and calculate the current flow through that resistance. So first thing that you have to do is go ahead, drop your sources. So once you click on library browser, this thing should open up. This library, you'll see several libraries. I mean, for me, I have several libraries, but I asked you to only install when you're installing MATLAB. Go ahead, only choose Simulink and this library, Simscape. So in Simscape, now out of these three, you go to electrical, and then out of electrical, you choose specialized power systems. So when you go here, drop down, you should see a drop down menu here. Then click on fundamental blocks. Here you should see the different sources like a DC source and AC source that you can start pulling from here and then dropping it into the blank page. first thing that I do is click on this, right click, drag it, and then drop it into the blank page. So I'm now dropped for the first element that I require. The second element that I require is a resistance. So you will not see a resistance block here, but what you see here is R, L, and C branch. So you can just take this and drag it. You can't copy it, I guess, but just drag it and use your right click, hold it, and drag it into the blank page. And then, because we are going to make use of only resistance, here you can click on branch type, go to resistance, and then, for example, let's choose 2 ohms here. And now I have a 2 ohms resistance, and I have a 10, for example, let's say if I have a 10 volts battery cell represented by voltage source here. I need to figure out what my current flow is in this diagram. So the next element that I want to use is a measurement block. So in order to do that, I go to control and measurements, and then here you should see current measurements. Alright, so now that's all that we require. We need a voltage source, a resistance element, and one block that measures the flow of current through the circuit. So first thing that we do is take the positive terminal, connect it to the positive terminal of the resistance, take the other end of the resistance, connect to the measurement block's positive end, and then the negative end connects to the negative end of the terminal. So all that I'm doing is holding on to my right click and then connecting each of these elements together. And this block does not do anything. It is just meant to measure the current that flows through this circuit. What you can imagine is, for example, you're just connecting wires from a voltage source to a resistance and then closing that loop. Okay, so all that you're doing is creating a loop here. And then next go to library browser. Here you should be, instead of going into anything here in Simscape, now we go to Simulink, go to Sinks, and then you put a scope. So a scope will allow you to look at the X and Y graph of the flow of current. And in order to simulate this, I can just choose a time of 1 second. And the reason why I'm choosing 1 second is because no matter what, with a constant voltage, a constant resistance, the value of current will be constant throughout the simulated period, and that's what we'll see here. So we'll see that you have a 10 volt source and a resistance of 2 ohms, and you should now know what the current flow should be based upon the Ohm's law that we use. Okay, so we'll have a issue here because there is one more block that you need to add in order to simulate this. That's called as power GUI or power GUI. Simply search for it, power GUI, and then you should get this. So again, just hold on to your right click and drag it to the blank page or the working page that you have right now. So once you have, just leave it as it is with the continuous option. You have other options, but we won't be using it. So just use it as continuous and now run it. Alright, so once you run it, you should now see a current of 5 amperes. And that's what you see here, right? 5 amperes. That's the voltage level, the current level on the y-axis, and the time. So as you see here on the x-axis you have time. So what it represents is that at 0 seconds, at 0.1 seconds, at 0.2 seconds, you have the same value, which is the constant value. So this is the representation of direct current, direct current means that with respect to time, the value of the any voltage or current will not change. But a sinusoidal will be oscillating in nature. That's what we'll see in the next slides or next coming slides. So how did we get to the value of current equals to 5 amperes? Is by simply using the formula, the Ohm's law that we just saw now in the lecture slide. V is equals to I times R, or I, whatever you say this, I times R. You know that the voltage here is 10 volts. That's what I've chosen here. The resistance is editable. I could have given any value here. So I chose R as 2 ohms, given by this Greek symbol ohms, right? So this is a representation for the units for resistance. And what I'm trying to figure out is the current that flows through this loop. So the current will flow through the wires, through the resistance, and through this wire, and come back to the negative terminal. So I'm trying to figure out what the current flow is through the loop. So for which I have to use this formula, I equals to V divided by R, which is equals to 10 divided by 2. That's 5 amperes, or 5A. You can just simply leave it as 5A, or if you want to put it AMP or AMPERES, you can have it anyway, but typically you can just leave it as 5A. Alright, so hopefully this is the simplest thing that we'll be doing, is by using the Ohm's law, we can figure out what the current value is. This was again just rearranging the terms. I equals to V divided by R. Alright, so just like for example, you can just, if you wanted to change this to 5, what happens? You have 10 and then you have 5, and then you should get a current of 2 amperes, right? Because 10 divided by 5. That's what we'll see here. Alright, so now we see a value of 2 on the y-axis, and that remains constant throughout the time period from 0, 0.1 to 0.2, 0.3, and up to 1 second. We have the same constant value. Alright, so hopefully that gives you a good understanding of a simple voltage source with connected to a resistor, and you close the loop. So just imagine if you didn't have this loop. For example, let's try this. Okay, if you did not have any loop, you would not have a current flow, which we'll see right now. Alright, so the value is 0, which means that unless you have a loop made, which means that you start with the positive terminal, connect a resistor, and have to connect it back to the negative terminal. So unless you do that, you won't have a flow of current. So the only way that you have a flow of current is by closing this loop. So I'll post all my, whenever I'm using MATLAB for you for demonstration purposes, I'll always post them on Blackboard so that you can just play around and get some more practice on these. Most of your homework will be based on MATLAB Simulink based circuit problems, so just be a bit familiar with it. I mean, the other alternative would have been for you guys to be doing probably working by hand, which I guess you won't prefer. So but you have to understand some formulas that we're using. But whoever does large scale electrical systems analysis and all, they would not, you would not have someone sitting down and doing calculations, or even an engineer does not do anything by hand, right? So they have to make use of circuit based analysis software like MATLAB or Simulink in order to analyze the flow of electrons or flow of power or flow of current, whatever you say that. So you have to have a basic understanding of the formula mathematics, but you can just replace that with understanding how to connect elements and then formulate a circuit and then figure out what the current flow is. Alright, so now let's move on to some more topics on resistance. Alright, so now we get into resistors connected in series and parallel. So a resistor connected in series would mean if you have, let's say, a positive and negative terminal for a resistor, which is not the right way to call it, but then if you, let's say, one end is a positive, negative end is the other end is negative, and then you have a positive and negative and a positive and negative of a resistor, and if you connect them, in series, the equivalent resistance can be simply calculated by adding up all the resistance. For example, if you had R1 equals to 1 ohm, or given by the symbol again, R2 is equals to 2 ohms and R3 is equals to 3 ohms. So the R equivalent is 1 plus 2 plus 3, that's equals to 6 ohms. Alright, a simple formula, right? It's just adding up all the resistance, and then you can simply replace that with one resistance value if you're doing an analysis, that's all. And then if you have to figure out what when you have a resistance connected in parallel, where for example you have positive, negative, positive and negative, and positive and negative. So if you're connecting all the positive sides of the ends of a resistance and negative ends of a resistance together, you'll call that the parallel arrangement. And one equation that you can make use of to calculate the resistance, equivalent resistance for parallel connected resistance, is this simple formula: R1 times R2 divided by R1 plus R2. So let's just imagine you had only two resistance value connected in parallel. R1 is 1 ohms, R2 is equals to 2 ohms, and then R equivalent is 1 times 2 divided by 1 plus 2, and then the formula is if you put this into the formula, 2 divided by 3 ohms. So that's how you figure out resistance in series and parallel. So I might ask you this in exams, like if you had two resistance connected in parallel, what is the equivalent resistance? If they are in series, what is the equivalent resistance value? And now let's get into electrical switches. Any electrical switches is any switch that you flip on and off to turn on off your lights, are similar to any element that you want to use in electrical systems to break off the flow of current or close to enable flow of current. When you're opening a switch, right? Opening a switch is in this direction. Just imagine this. If you had, for example, if you had a wire connected and you want to allow flow of current, you have it in the closed position. When you have to break the flow of current, like for example, if you have a current flowing from one end and you want to stop the flow of current in the loop, all that you have to do is open the switch. So in terms of electrical parameters, when we say that the switch is open or simply open circuit, the resistance is infinite, which means that you have infinite resistance, because it essentially means that you have air as the material, which typically has infinite resistance and will not allow free flow of current. And the only way that you can allow free flow of current is by closing the switch. So when you close the switch, the current flows from here, gets to here, comes down, and then flows in the other end, flows to the other end. So if you have to break this, simply just open the switch. And when you talk about closing the switch, typically the resistance is equals to 0, which means that when you have 0 resistance, whatever current enters will be equals to the current output. So just remember these terms: open circuit and short circuit. An open circuit is usually for a switch that is open by simply opening the switch. You have to close, you allow the free flow of current, right? So again, if you have to switch off a light, right, you're simply opening the circuit, and you have, when you want to turn on a light at your home or anywhere, right, you just have this switch closed, and then the resistance is equals to 0 ohms. Alright, so now let's move on to the next element, which is inductor, and the property of inductor is called as inductance. Similar to resistor, the property of a resistor is a resistance, and a property of inductor is inductance, and for a capacitor, which we'll see, is a capacitance. But inductance is the property of an inductor. Inductor is the element. Alright, so now let's look at what an inductor is. An inductor can be viewed as an energy storage device which can be applied in DC and AC applications. And typically the energy, when we talk about being stored, it's stored in the form of magnetic field. And the equivalency of an inductor in mechanical domain or mechanical systems is a rotating flywheel, right? Just imagine a rotating mass is trying to store energy, right? So this is, for example, a flywheel trying to store energy in the form of momentum, right? Or just imagine your vehicle which is trying to move, so it has an energy built up through momentum, right? And a rotating mass is a flywheel, and that's what is equivalent in terms equivalent to inductors in electrical terms. And what this means is that an inductor, which is sometimes an inherent, or most of the times it's an inherent property of a cable or a conductor, opposes the flow of current. So the change, any change of flow of current is opposed due to the property of inductance. Or if you have an inductor already, if you want to intentionally want to connect an inductor, and there are by purpose, there are sometimes electrical engineers will add on inductors. We'll not get into why, but all that you have to understand is that even if you have an inductor that is an existing property of a line, or if you want to add a new inductor to the line, it will oppose the change of flow of current. The same way, a flywheel will change the flow, or any attempt to stop the rotating flywheel is opposed by the momentum. So the same way, any change in flow of current is opposed by an inductor. Okay, so hopefully you understand this, the property of an inductor in an electrical line. And this is, anytime when we talk about magnetic circuits, they are typically associated with inductors. And for example, just like a wire or conductor, if there is a magnetic field that is built up around the cable or line, you call it as an inductive property. So in this case, you do not have any turns, right? You do not have any turns. But intentionally, if you have several turns, there will be a higher magnetic field that is built up, and you can call this as having a higher inductance than compared to a straight line. And that can be explained by this formula, right? L is equals to mu times n square times A divided by L, where mu is the permeability of the medium, n square is the number of turns. So if you have a higher number of turns compared to just a straight line, you'll have a higher inductance, L. So the inductance is given by the symbol L. This is the symbol, and the units for L, or in the inductance, is henries, or simply we can just leave it as H. So anytime you want to calculate the inductance, you have the units are end up being henries or simply H. And the energy stored in an inductor can be calculated as half Li squared. So for example, if you have an inductance of 0.1, and let's say the current that flows through the conductor is 2, simply put this in this formula, half Li squared, and then you end up with 0.2, right? 0.2. You have 2 square on the numerator, 2 in the denominator, you end up with 2. After you cancel the numbers out, then you have 0.2. And typically the energy units are joule.